Morning from here in London. Thank you for joining us for today's webinar with an oil and gas focus. Today's topic will be looking at simulation for safe and reliable oil and gas operations and maintenance. Just some bios and then we'll get things kicked off. We have three speakers, if you will, today. We have Alex Reed, who's a Global Director of Industries Group. We are delighted to have Alistair Gill, who's the Vice President, Advanced Engineering from Wild Well Control, Inc. And we also have Vincent Lister, PhD, who's a Technical Pre-Sales. And Alex's and Alistair's presentations have been recorded. I will be playing those as video, but Vincent's demo and work will be live. So I'll just give some brief bios and then we get things underway. Alex has both undergraduate and graduate degrees in engineering and CFD, as well as an MBA in over 15 years at Siemens PLM, formerly CD Adapco. He has worked as a project engineer, run customer support team for Northern Europe, and spent the last 10 years leading our operations in Houston, Texas. Alistair is Vice President of the Advanced Engineering Department at Wild Well Control, which is an emergency planning and response company within the oil and gas industry. The Advanced Engineering team provides advanced simulation expertise in support of Wild Well's control, emergency response and planning activities. And finally, we have Vincent, who has a PhD in chemical engineering from the University of Cambridge. He has worked at several chemical process companies such as DuPont, Akzo Nobel, and Huntsman. He currently works in the pre-sales team in London, focusing on oil and gas and chemical processing. Okay, now that we have all of the bios over with, I would like to play the video presentations from Alex Reed, followed by that with Alistair Gill.
Okay, thank you, Jay. So I'll just give a quick introduction to the use of simulation for safe and reliable oil and gas operations and maintenance. And I'll quickly touch on some of the business drivers in the oil and gas industry, some examples of what that means and how simulation and CFD simulation is helping, and then finally try and link that into the broader Siemens vision, which is for simulation, which is all based around SimCenter. So there are various things going on in the oil and gas industry today. Obviously, the most obvious one that's been with us for a few years is the relatively low price of oil and gas, and that obviously has had significant implications on the industry, ranging from concept development, project execution, right through to operation. All of that's being reevaluated to be sustainable in the current kind of market conditions. The second area is really the digital transformation. So how can people use digital technologies, which can range from the kind of Internet of or industrial Internet of Things, pulling data from the field to do analytics on them in order to improve our decision making, through to things like predictive analytics, which is more the topic that we're going to talk about today. And then, third, the third one is very much linked to the first, which is a focus on efficiency. So how can we make sure that our operations, whether that's related to production or the workforce, are as efficient as they can be? And the implications for those are, there are many of them. There's a survey done by PwC a couple of years ago, which indicated that a very significant proportion of the oil and gas industry is looking to either increase or start investing in this kind of digital technology for a variety of different reasons, which can range from trying to maximize its impact. So can they adopt or use this technology before their competitors, through to the things we're going to be talking about today, which is improving the reliability and obviously the safety of operations. So to apply that to a specific example, this one's from Technip FMC, where they're designing subsea equipment, and obviously one of the operation and safety concerns is erosion. So as you have solid sand particles traveling through the equipment, as it impacts the surface of that equipment, it can gradually erode that equipment, and ultimately you'll end up with a failure or a need to replace that particular piece of equipment. So they've used CFD simulation combined with with intelligent design space exploration to very quickly understand their design space and have the ability for a given pressure drop, so a given design condition, they can minimize the amount of erosion that occurs. And by automating the simulation process, they've been able to significantly reduce the amount of engineering time it takes to achieve that. Then a second example is to do with flow-induced vibration. So again, there are industry standard methods for evaluating flow-induced vibration. They tend to be very conservative, so that can lead to either kind of additional cost and over-design, or potentially issues in the field if you don't identify the problems beforehand. So there's a significant increase in the use of CFD to do detailed modeling of the flow through piping networks, and obviously the end result of that is to provide the structural response and then ultimately the stress, so that you can understand what the potential for failure is, and try and deal with those issues by reinforcing them in the design phase rather than having to deal with them in the field. So that's a quick overview of some of the drivers in the oil and gas industry, how CFD simulation is being used to help address them, with a couple of examples. And obviously now, as we're part of the Siemens organization, we're increasingly linking into this to the SimCenter kind of portfolio. And really the goal for SimCenter is relatively simple. So if you look at most engineering organizations today, they perform 3D simulation, whether that's CFD or FEA. They've got testing information. They've got data from previous products that they produce, or data from the field. But it often tends to be very disconnected, and there's not much coherence across these different disciplines. So one of our goals is to try and help people bring that information together into what we call a performance digital twin. And the examples that Alistair will give in a moment will really show very concrete examples of the benefit of being able to link CFD simulation with physical testing to build confidence in the modeling, such that you can then apply it to other scenarios, as well as linking with other types of CFD simulation. So again, to give a couple of specific examples, one is doing fluid structure interaction. So we're linking StarCCM Plus with the NX Nastran, so the structural capabilities within the SimCenter environment. And then obviously, as companies try and develop or have this coherent digital thread through their engineering processes with their PLM system, we're linking or improving the ability to link simulation data into that digital thread, so that your performance of the digital twin can be understood and tracked and managed throughout that whole process. So that's a quick introduction to some of the drivers within the oil and gas industry, how CFD simulation applies or is relevant to that, and then how does that fit into the bigger picture of linking with other forms of analysis, and as well as PLM systems. And with that, I'll hand it back to Jay.
Hello there, this is Alistair Gill. I'm the Vice President of a department of wild well control called Advanced Engineering, and I'm going to present today some of the uses of StarCCM Plus that we use in our day-to-day work at wild well control. So this is what basically I'm going to cover. I'll give you a very quick introduction to elaborate on what I've just told you about advanced engineering, cover a few examples of how we use CFD and StarCCM Plus in particular, and then I'm going to focus on two particular things, something to do with subsea plume studying and something called cryogenic freezing. I'll go through that and explain how we do that. So fundamentally, advanced engineering is a department within a well control company, and we specialize in numerical simulation of all different kinds, CFD predominantly, but also structural analysis, across a wide range of topics. So anything to do with fluid dynamics, obviously, heat transfer, erosion, fire modeling, structural analysis, various different things, all supporting well controls, basic operations. Well Control is a emergency response company responsible for reacting to oil field blowouts and other pressure control problems where the client gets themselves into difficulties. And then we contribute to that effort by providing our advanced engineering services. Two things I've mentioned we're going to talk about today to do with risk management. A lot of the effort that goes into emergency response planning is all about understanding the risks you're taking when you're drilling an oil well. And I'll talk about some of the things we do to support that process, and also something we call special services, which is where a department within well control help repair oil field equipment by providing a temporary pressure barrier by using cryogenic freezing. So those are the two areas I'm going to touch on. So we are an emergency response company, and if something goes wrong, then clients often call the red phone, and our emergency response team, first responders, go out and help deal with whatever problem the client has, whether that's a minor pressure control problem or a catastrophe. But before we get anywhere near there, we spend most of our time trying to prevent that happening in the first place, and also helping clients prepare for an emergency should that occur. And we do that in a number of different ways. So, for example, if a blowout occurs offshore, subsea, then the first response team has to know something about the hazard they're going to face and how the actual blowout scenario is going to interfere with their attempts to bring the well back under control. So that includes things like subsea plume analysis using CFD and gas dispersion to try and understand what hazard is being posed. We also then look at, in some of the response actions to try and bring a well under control, we might look at trying to cap the well. And so we use CFD to look at capping processes and so on, and also looking at fire radiant heat and how that affects both the surroundings and the emergency response team. So we use CCM Plus for all of those things. So if we stick to the emergency response plan to start with, looking at what are the safety implications for the emergency response team from a blowout. So this is specifically looking at what is the threat to the personnel that are trying to bring the well back under control. What is the threat to them? This is not looking at the wider environmental concern of a blowout when it's offshore. This is specifically looking at what happens to oil and gas. Do they cause a problem for the response team? So looking at what the safety zone may need to be on the ocean surface when we're positioning various assets like relief rigs or intervention vessels on the sea surface above the well. Are they going to be threatened by hydrocarbon gas or what have you? So that's what we're trying to understand, and that's why we do CFD analysis. So we're looking at a subsea release from an accident, whatever form that may have taken. We're releasing oil and gas into the ocean from the seabed. That then has to then transport through the ocean to the surface, and in doing that, it may or may not pose a flammable threat or a toxic threat to the surface assets that have been deployed to try and respond to the well. So we typically break this problem into three: a zone near the seabed, which is right down at the source location, the rest of the water column, and then up into the atmosphere. So if we look at what's going on down at the seabed, we may be trying to cap a blowing well, and the question we get asked is, can we cap the well successfully, or is there going to be any issue landing a capping stack on the blowout? So we can examine that scenario using a CFD analysis, using CCM Plus, doing a dynamic fluid structure interaction. So this example here is showing a model we have of one of our capping stacks interacting with the plume as it's emitted from the blowout. And the CFD analysis there is accounting for all the various forces acting on the 6 degree of freedom model of the capping stack, which is suspended from a lifting wire and reacts to the forces acting on it, so buoyancy, ocean current, and of course the jet coming out of the well. And we can examine various different scenarios to see whether there's going to be any difficulty in latching a capping stack onto the wellhead. So that's one of the first uses we use CFD for. Then, assuming we can actually latch a capping stack, the other question that is relevant is what is coming to the sea surface, and is it flammable? And will that interfere with capping operations, or for that matter, any other surface operations like drilling a relief well? So we do subsea plume analysis using CFD to work out gas concentration at the sea surface. So the example you see running there is a multi-phase CFD analysis of a gas plume rising through the water column and hitting the sea surface. And we run various different scenarios to account for different discharge rates, different discharge compositions, what the ocean current's doing, and other things like whether the gas is dissolving in the ocean. So there's a mass transfer mechanism at work often where what comes out of the seabed does not necessarily reach the sea surface. So these are all things that we need to account for in our CFD analysis. And anybody familiar with multi-phase CFD knows that you really do have to have a good handle on whether the analysis is valid or not. So we spent quite a lot of effort in trying to validate these analyses, and we're members of a joint industry project that's been carried out over the last few years, carrying out large-scale experiments to validate the CFD models that we're using to predict these subsea bubble plumes. So what you can see here is an example of some of the first large-scale experiments that were carried out in a fjord. So this is offshore, but in inland water, in about 100 feet of water depth. And we're releasing compressed air from the seabed and then using the instrumentation in this gantry to monitor what the bubble plume is doing at various different stages. So what this animation or this video is showing you is that exact test in the fjord. So we're releasing compressed air from the seabed, and at different water depths we can monitor things like bubble density, bubble velocity, bubble size as the gas rises up through the water, and then obviously we can see what's going on at the surface. So as the bubble plume rises to the surface, it's dragging an amount of water with it. The gas breaks out to the surface, and then the water flows radially outwards, causing that typical radial flow, which can in itself be an issue for interacting with the well. If you've got a surface asset trying to lower a capping stack and you have these very strong outflows, then station keeping can be an issue. So all of these things we can then predict with CFD, provided we've got confidence in the CFD model, and that's what these experiments are helping to provide. And then further offshore into much deeper water, further experiments. In this case, this is a methane release, and they're in a certain location in the North Sea, in about 500 feet of water. And you can see there a time lapse of the gas breakout as it evolves over time. So on the right-hand side, you can see a time history of the gas evolution, and then on the further right, you can see images taken from the CFD, which is predicting the same release. And you can see they give a reasonably good comparison. So the next stage of the JIP is looking at further improvements to the mass transfer mechanisms that are at work. When you release the gas in the ocean, it doesn't all get to the sea surface. So we're providing further experiments in the laboratory to work out more information about the mass transfer mechanisms. And then there's plans for further offshore experiments. And of course, while this is all going on, we're continuing to evolve and improve the CFD models that are predicting this behavior. So that's what we use CFD for when we're looking at subsea plumes and emergency response plan support. The other thing I wanted to talk about today was our use of Star CCM Plus to model cryogenic freezing. We often want to repair oil field equipment, valves and so on that are not functioning. And in order to provide a pressure barrier, we look to try and freeze the content of the pipework upstream of the device we want to repair. So we use cryogenic freezing to do that. So I'll just explore how we do that and why we do that and what we use CFD for. So for example, if we have a series of valves on a tree, we may want to remove one of those, but obviously they may have pressure behind them. And so we want to provide a barrier. And one of the few ways you can do that in certain circumstances is by creating a ice plug in the bore to provide a pressure barrier so that would then allow us to remove that valve. So this occurs on various pieces of equipment on trees and wellheads, and we use liquid nitrogen particularly to remove the heat from the object we're freezing, which will eventually freeze the core into providing a pressure barrier. And we do that in a number of different ways, using what's called a canister approach or using a coil system. It depends on the geometry that we're trying to freeze. So what this animation will show is just step us through this cryogenic freezing process, first of all, before we get into the CFD. So we have a Christmas tree, for example. There's thousands of these dotted around North America or elsewhere in the world, and we may want to freeze the entire wellhead. So we want to maybe remove the entire tree. So we use a canister jacket, which clamps around the well, provides us a pressure seal, and then we pump liquid nitrogen into the base of that, and we control the flow rate of liquid nitrogen to vent off gaseous nitrogen at the top. If we see liquid nitrogen coming out the top, we know we have too high a flow rate, and we can control the flow rate, so we just see gaseous nitrogen coming out the top. And what that's doing is converting the liquid nitrogen to gaseous nitrogen, is removing energy, heat energy from the well, and as it does that, it freezes. As the freeze process occurs, we bleed off pressure from the various annuli, which helps us prove we have a pressure seal. And that provides a pressure barrier, and we can then start safely removing valves and so on while we have the liquid nitrogen flow controlled to maintain the ice plug, and allows us to take equipment off and repair. Here's an example of a canister repair underway. So this is in a excavation trench, exposing the well underneath the wellhead and venting off nitrogen. And that in itself causes us an issue, because you have a potential confined space hazard there. So the guys that have to interact with this well often have to be respirated up to protect themselves from suffocation and so on. But you can see the process of how we're cooling the well to provide the pressure barrier. Now, what we want to use CFD for is to predict that process, so we have a better understanding of what will happen when we carry out these cryogenic freezes, when we start to interact with more and more unusual situations. We want to be able to predict what's happening in circumstances that we've never approached before. So that's the purpose of using the CFD. It fits in well with the company culture of making sure we engineer our well control solutions. So the example on the image on the right shows a coil approach, where you're pumping the liquid nitrogen through this coil, which is wrapped around the well. So depending on the geometry, we may not be able to fit a canister, so we use this coil approach. But it does the same thing. So we may have a multi-string configuration. This is a typical wellhead. And so we're going to be freezing through various steel casings and annuli, with the primary objective is to freeze the appropriate pressurized space, whether that's the production bore or one of the annuluses. We want to provide a pressure barrier, so we're wanting to predict what will happen, and we use CFD to do that. So we're predicting the freeze time, the freeze plug shape, and any impact that freezing process may have on the steel components. So we may be coupling CFD to other numerical analysis like finite element analysis. So we have a relatively straightforward looking CFD model. This is a simple axisymmetric representation of what's going on in the well. With the center line shown, we can see the main bore is fresh water in this case, and if it isn't fresh water, we often displace the hydrocarbons to allow us to put a material in there that will freeze. And then in the other annuli, there could be brine or could be diesel, whatever. Again, we may need to try and displace or add in a material that we know we can freeze. And so we apply a jacket around that and start to pump liquid nitrogen through it. And we're using the melting solidification models within Subsea CCM Plus in order to allow us to simulate this. The early work we did was based on a conduction model, and then we've developed it further to properly account for convective heat transfer. So if we take a real simple example of a simple pipe, steel pipe, being cryogenically frozen, if we ignore convection initially, we can see the freeze process occurring. Anything red is a solid fraction of water, so ice. And we can predict the the freeze time based on classical calculations quite accurately if we're ignoring convection. But we know in reality we don't have a conductive problem, we have a convective problem. So we can look at different environmental cases. In this case, we have a relatively cold ambient temperature, and so we can simulate the freeze process. Again, this is a canister jacket type freezing process. Then you can see here the progression of the temperature as the well is cooled down, and the progression of the freeze front as the portion of material is changed from liquid to solid using the solidification model. And as we progress time, you can see the progression of the cool into the well, making the solid fractions extend all the way through the core of the well, creating a pressure barrier, an ice plug. And we can then see what the ice plug shape looks like and get a feel for what the total freeze time will be. This is important for the guys to know how long we're going to need to be running nitrogen. So they need to obviously have an appropriate volume of nitrogen available to them. And so if they don't know how long it's going to take to freeze, that obviously can cause an issue. So if we then have a much higher ambient temperature, a lot of the work we do is in the Middle East, for example, where you have a very high ambient, then that changes things. It takes longer to freeze. You've got a lot more thermal energy stored in the well, and obviously the temperature and the environment makes a difference to the freeze time. But it also affects the freeze plug shape, as I'll show here. So here's a progression of the freeze process again, this time after 15 hours of running the nitrogen. Then in 30 hours, you can see it's taking a lot longer than previously because of the extra energy we're having to remove from the well. But also you'll notice that the freeze plug shape is subtly different, and that the ice plug is no longer symmetrical. So the ice plug shape at the base of the freeze zone is different to that at the top, and that's all to do with convective heat transfer. We have a warm well below our freeze jacket, and so there's convection occurring underneath the freeze zone, which affects the base of the ice plug shape. Whereas above, we would stratify the flow because we have cold below hot, and so we have a relatively similar freeze plug shape to what you would expect to see regardless of what the environment temperature is. But it does affect the base significantly, and it takes an awful lot longer to freeze when you have a high environmental temperature. But we can validate this against experimental tests. So the special service guys have run hundreds of freeze jobs before, so we've got a good data pool to compare to, and so we can validate the CFD simulation, and we get a quite accurate result in terms of overall freeze time, certainly within a few hours, which is all the guys really need. It doesn't need to be more accurate than that. But then I also mentioned structural response. If we're cooling steels down to cryogenic temperatures, then we have to be wary of what that may do to the steel. We obviously don't want to compromise the well by providing the temporary pressure barrier. So we use finite element analysis to look at what's going on when we create these ice plugs. So we're creating an Abacus FE model that we map temperature data from our CFD analysis to, taking into account the non-linear material behavior of ice and so on, and the discontinuity in the thermal expansion of water as it approaches freezing. So as you freeze the water, it expands significantly, and obviously that has a couple of negative effects on the surroundings. It produces pressure in any trapped water space, as well as creating some pressure on the pipes where the ice plug forms. But more important is the confined pressure caused by the expansion of the water as it freezes. But we can account for that in these FE models. So basically what you're seeing here is a FE equivalent of the CFD model, particularly focused around a casing coupling. So we can predict what the ice behavior and freezing process is going to do to the steel as the ice plug expands and increases the pressure in the water and so on. So we can also look at the likelihood of having poor cement quality in some of the outer annuli. If we have a poor cement job that may have water trapped within it, then that can potentially cause a problem, because if you can't bleed off the pressure as the ice expands and pushes the water ahead of it, then you can generate significant pressure and cause potential damage to the steel. Anybody that's had a burst pipe in the wintertime might sympathize with that process, and one of the reasons why I was always told as a lad to keep a tap dripping in the winter to bleed off the pressure as the ice freezes. But this can be a problem if we don't predict what's going to go on if we're freezing a large well with a large annulus full of dodgy cement. So that's one of the reasons why we want to also explore this with CFD. So we can look at the stresses introduced as a result of the freezing process. Here's, for example, the case I mentioned of the coupling, but also in the outer conductor and surface casing. Are we going to introduce significant plastic strains or not by the freezing process? Typically, we want to avoid that. You do not want to strain the steel beyond the elastic range if you have them cooled to cryogenic temperatures because of the risk of brittle fracture. So this is part of the reason why we want to do these CFD simulations is in order to provide us with information about, are we going to harm anything when we create these pressure barriers. So we can see in different cases, different amounts of trapped water do different amounts of damage to the casing. And what this allows us to do is warn the special service team about what they may need to check before they apply the jacket and start freezing. They may need to do some diagnostic work to try and understand the quality of the cement in the various annuluses, to try and predict whether there is any trapped water before they start freezing. And if there is certain levels of trapped water, what do they do about bleeding that confined water off first before they freeze? So just to conclude, the point of doing this CFD is to provide better insight into what's happening. We always want to know in advance what we're going to do in a live operation. We don't want to harm the well. We don't want to cause any safety implications for the special services teams. We need to know how long it's going to take to freeze a particular well so that we have the appropriate amount of nitrogen on hand, and then allow us to examine different scenarios on paper so that we aren't working on a live well in the field without understanding what's going to happen. And one of the things we're looking forward to is in future releases of Star CCM Plus is the ability to not have to use a third-party FEA tool. At the moment, we need to account for nonlinear material behavior, which forces us to use a third-party software. But as the solid mechanics side of CCM Plus develops, we'd imagine we'll be able to do all of this inside the CFD tool, which is obviously better for everybody. So that's all I had to say today. If anyone wants to ask any questions about it, feel free to contact me, and I'm sure we can make contact details available. Thank you.
Okay, hi, good morning, good afternoon, good evening, everybody. So today I'm going to be talking about how we can discover better designs faster using Star CCM Plus, our CFD tool. And to help me in that, I'm going to use a case study of a Christmas tree, a Subsea Christmas tree. And as you can see in the top left here, what you're looking at is an animation of a typical cooldown situation when you're shut off your production and you want to see how the fluid is behaving in this cooldown. So in this demonstration, I'm going to be talking about Subsea Christmas tree performance. So we're going to use Star CCM Plus here to gain an insight into the subsea hydrate formation and the heat and transfer within our Christmas tree. On the bottom left, you see a typical subsea Christmas tree. These units are ubiquitous in the oil and gas industry. They are sort of typically used to to control your production fluid for flow assurance reasons, and basically to monitor and control the production materials. So we take our real-life product here and we build a digital twin within Star CCM Plus, which is what you see here, and we did this using our 3D CAD tool within Star CCM Plus. What I'm going to show you today is how we can quickly and simply generate and test a design variant. So one of the things that's going to be crucial to understanding whether subsea hydrates are going to form or not is to understand how much insulation we need to put around our subsea Christmas tree. So we're going to create a design variant where we increase the value of the insulation by decreasing the thermal conductivity of the material surrounding our Christmas tree, and see what effect that has on our temperature profile. What you can see on the top right here is an animation of the flow path, and here we're gaining information into exactly how the flow is behaving, and we can see here in the bend region exactly where the flow is impacting, which might be useful for flow assurance or erosion reasons. Lastly, I'm going to just talk quickly about how we can automate this change, this insulation change, to search the whole design space to come up with a design that might be a compromise between getting the best thermal performance while maintaining the integrity of the Christmas tree. So just to move on here, you see the flow in the bottom right moving up the Christmas tree and to the right, and a stagnation zone above the top left there, indicating flow that's really stationary and might be subject to where these hydrates might form. So let's talk about this virtual prototyping process within Star CCM+. So as I said, we start much as you would with a normal prototyping process by building the geometry. So we take our 3D CAD within Star CCM+, but you could also import it if you've got some available, and then we generate a numerical representation of that, which is known as a mesh. We then test our model by defining the relevant physics for it. So for this case, we're going to look at a steady state simulation and look at the conjugate heat transfer. So that's heat transfer from our C, our environmental C, through our insulation surrounding the Christmas tree, through our steel, which is obviously the casing, and then into the process fluid. We're going to be looking here, because we're interested in hydrates, we're going to be looking at the worst case scenario, which is when the production fluid is just gas. Now, we're going to change this in a manual way. We're going to change the insulation value, but we could also do this in an automatic way. And what you see here, each of these blue dots represents a different value of the insulation, and we're plotting on the left-hand side the performance of our subsea heat, our subsea unit. The last step in this process is to assess our simulation data, so to understand exactly which of our designs are performing well and which aren't, and to understand any trends or data trends within the system. So we're going to join our simulation at this point here, where I've conducted a single test. So I'm now going to move into Star CCM+ here. So here's the geometry on the left-hand side of Star CCM+. Now, as you can appreciate with this type of geometry, it is quite complicated. So on the right-hand side, what I'm going to do is I'm going to build it up step by step. So first of all, I'm going to highlight the production fluid. So here's the process fluid inlet coming out and the process fluid outlet. Surrounding the process fluid, we have our steel here. So this is we're going to be modeling the heat transfer through the process fluid and how that matches to the steel, and then finally how that goes through to some trapped seawater that we have, which has got in through the insulation. And then we have an insulation layer which surrounds everywhere. So just zooming in, you can see here we've got our process fluid, our steel, our insulation, and here's the trapped seawater. So hopefully that gives you a little bit more clarity as to how the model is built up. So now that as I say, we've run through one simulation, we can first of all interrogate the flow field. So here you see a plot of line integral convolution, which shows exactly where the flow is traveling. So if I hit play, we can see the recirculation zones here in the trapped seawater, in which we see that the flow is not moving and is solely trapped. We also see here, if we look at this bend region here, that we have a strong acceleration and a region here where we've got another recirculation zone. So from a flow assurance perspective, we might be interested to understand whether we should be mitigating this by chamfering or filleting the corners of this to create a more even flow. We also see we have some clear stagnant regions on the top left, and also in these regions here. So that's looking at it from a flow assurance perspective. We can also look at the streamlines to gain a much more visual understanding of exactly how the flow through our oil rig occurs. So you see now we've got the flow coming from the production from the well up, round and down to the right here. Now, as I said, this is a conjugate heat transfer simulation, so we can look at the temperature profile within our subsea Christmas tree. So you see the production fluid here is coming in at 50 degrees Celsius with a flow rate of 5 meters per second, and then it is transferring heat here to our steel and through the insulation here. So in this case, we see that we're getting quite a large temperature profile across the simulation, which goes from 50 degrees here through right down to almost the seawater temperature, which in this simulation is set at 5 degrees. We can also look at the temperature within the solid section. So on the left-hand side here, you can see that I've split out the various parts of our subsea Christmas tree. So on the right here, you see the fluid path, and we can see the high temperatures here. In the middle, you can see this is looking at the temperature within the steel, and you can see here that we've got a temperature of around 14 degrees C, and we're able to interrogate also how the profile of the insulation is, which is almost at 5 degrees, indicating that we've got not a great temperature difference from 5 to 14 across the insulation, indicating that we could do better. So one of the great things about conducting a virtual test is that we can quickly change our design parameters. In this case, I have my properties of my insulation here, which is being modeled as a solid with modeling the energy transfer. And we're going to change the thermal conductivity, which at the moment is set to 2. We're going to change that to 0.2. And now what we can do with StarCCM Plus is we can carry on running the simulation, and we can begin to see how our temperature profile changes within our domain. What we're looking to see here is that because I have decreased the value of thermal conductivity, effectively what I've done is I have increased the effect of the insulation. So we expect to see a greater temperature drop. So now you see the temperature in the insulation layer has risen from what it was about 14 now to about 23. This helps us because it helps us to identify regions where we expect to get cold or hot spots, and therefore from that data, coupled with our knowledge of stagnation regions, we can begin to understand where we expect to find these hydrates performing from this virtual test. We can continue in this manner by changing the simulation as it's running to say 0.1 to see a greater effect of the insulation. So you can see how we can quickly test and generate and test these design variants. So I'm going to move back to my presentation now just to speak about an extension of this. So in this case, we were solely looking just at the conjugate heat transfer, but within StarCCM Plus, we can also use this flow data that we've got to gain insight into damage areas, areas that might be damaged by erosion. And what StarCCM Plus will give you is the ability to predict local areas where you might expect damage in terms of damage rates. So how much material are we removing per unit area per second? And we can use this to predict these areas, for example, here, which we talked about earlier with the poor flow assurance, and here, and identify whether we might need to thicken the steel or the pipe thickness in this area, or even to increase the monitoring from a maintenance perspective. Okay. So just a few closing remarks now before I finish. What you're looking at here is an animation of the particle tracks. So here we've injected some particles, and you can see why there was so much damage caused in this region here is because the particles are strongly accelerated as they go around here. So what I've shown you today is how you can gain insight into the product performance with virtual prototyping in StarCCM Plus. So what we've been able to do is to identify regions of where there are hot spots, cold spots, where the flow is not very uniform and where this might cause problems for us in terms of erosion or hydrate formation. I've also shown you how we can quickly and cost effectively build and test design variants. So we did that in this case by changing the insulation thermal conductivity, which enabled us to look at what would happen if we picked a different insulation. We could also do this by changing the geometry and rerun the simulation with just 2 buttons, also 2 clicks. Most of all, though, StarCCM Plus will allow you to drive innovation and discover better designs faster in your oil and gas applications. Thank you very much, and that concludes my demonstration. So over to you, Jay.
With that, this session is closed. Goodbye.